But all right, TT, my next class.
So, yeah, that one we'll look at real quick before we start doing the reactions. Uh-oh. Where were we? Oh, we were already looking at it right here.
Yes, sir. We were already looking at it, but we never
We didn't finish it.
Yeah, we didn't do the 4n plus 2. So I was like, I didn't know if we had to count that electron or not.
Well, it's not there's no electron up there. That's why it's positive.
Right. Okay.
Yeah.
I was just
So
making sure.
Yeah, just count the pi bonds. Right. So it'll be for this cycloheptatriene cation, it'll be, hold up, let me fix my pen. Sorry. 4n plus 2 will be 6. So n will be 1. So that meets the the 4n plus 2 rule. Is monocyclic, is planar, and is fully conjugated because there's a p orbital on every carbon. So the cation is aromatic, whereas the neutral molecule isn't. Right. And I think when we were talking about this, we were talking about where the cation came from. And it's basically if you take the neutral molecule and abstract the hydride. Wrong pen. So here you remove, hold up 1 second. So you remove H minus. Right, so you remove a hydride and then you can get to that cation. So yeah, that one is, the cation itself is aromatic, but the neutral species isn't. Right, and then we have that right here, that is non-aromatic. Right, hopefully that answered that, or made it make more sense.
Yes, sir, it did.
Okay. All right, let's jump in to these reactions. And I'm going to start out with, this is in the video, so it's going to be a little redundant, but I want to start out with the bromination reaction. And then what I'm going to do is kind of weave in the other information, right? So the bromination, I'm going to tie that in with the substitution and with the directing effects, right? Is one of the things to know about aromatics is that, number one, they're not very reactive, right? Again, we said that benzene is like the perfect molecule. So if it's perfect, it doesn't want to disturb that perfection, so it doesn't react unless it's in the presence of a catalyst. So you'll see all of these reactions of benzene happen in the presence of some type of catalyst, right? So like if you're doing a halogenation, you're going to use like iron bromide or iron chloride. If you're doing alkylation, then you'll use like aluminum. If you're doing acylation, you're going to use aluminum. And when you look at these reactions, this is only one class of reactions. This class of reactions is what we call electrophilic aromatic substitution, right? There's another class of reactions of aromatics called nucleophilic aromatic substitution. So in this particular case, the ring is acting as a nucleophile. Right? And if you look on the ring, now let's go ahead and clear this up immediately before we get into anything further. All right, all of the carbons in that ring are sp2. So they only got one hydrogen on them. All right, so don't get confused thinking that this is the same as a cyclohexane, because it's not. The pi bonds in the ring mean that every carbon on there only has one bond, one additional bond to it. That's not seen, right? It's hydrogen. So when you're doing this substitution, sorry about that. When you're doing a substitution, you're actually substituting the hydrogen for whatever electrophile you're adding into the ring. Right, so the ring is the nucleophile, and then the other part of that is hydrogen that's substituted. All right, any questions about that before we go jump in? All right, so I'm gonna put another, like a new page in, because there's no way to cram this mechanism into here. And then I'm gonna copy this. Actually, you know what? I'll just write it. What's today? The 9th? Yeah.
Yes.
All right. So nucleophilic, aromatic, substitution. All right, so let's do the halogenation first. And the reason I'm doing this is because all of these reactions are going to follow like a similar mechanism, right? If you saw is that rain too loud?
No.
Okay. I got a feeling that sorry, I wanted to stay out in the garage and work, but that's okay. All right, so with this nucleophilic aromatic substitution, you're going to find out that the mechanisms are very similar, even though they're not identical. There's going to be some type of activation step. There's going to be a nucleophilic attack of the ring. On the activated electrophile. And then there's going to be a final step, which has to happen, just because anytime you have an aromatic compound, it's rare that you'll be able to break up the aromaticity. So you're going to reestablish aromaticity. Right, it's the same 3 steps. Same 3 steps. All right. So when we look at the halogenation reaction, I'm just going to write it down here. So we take this plus Br2. And then we use iron 3 bromide. Right. The product is here. Then I'm going to put the side products, because when we go through the mechanism, it'll help it make more sense. All right, iron 3 bromide is a catalyst. And what we know about catalysts is that they never get used up, right? You always regenerate the catalyst, and it can be used again in another catalytic cycle, right? So anytime you have a catalyst present, you're going to regenerate it. right? Always regenerate your catalyst. So if we approach this like according to the 3 steps we just looked at, the first thing that happens is activation. Right, so you have to activate your electrophile. In this case, you're going to form like a complex with iron bromide, with the bromine molecule. So here's Br, that, and then that's going to form a complex right with iron bromide. Notice that I didn't draw this as a covalent bond. It's simply a coordinate, like it's like a coordinate covalent bond. So the lone pairs on bromine kind of donate into empty orbitals on iron, and so now you form this complex.
I have a question.
Go ahead.
So this is for the nucleophilic aromatic substitution or the electrophilic?
Electrophilic.
Okay.
Yeah, we're not going to cover nucleophilic. It's the same principles, but they're reversed for nucleophilic. So whatever principles apply to electrophilic aromatic substitution, for nucleophilic aromatic substitution, they're reversed.
Yes, sir.
So the ring is the electrophile, and then you're adding a nucleophile. So everything is reversed. So once you make this complex, again, you have you're going to have some polarization of that bromine bond, and that's what activates it. Right, that's what activates it. So once that's activated by the catalyst, the next step is the nucleophilic attack of the ring. Right, so here's my ring. And it's actually going to attack that complex. All right, so I'm going to take this pi bond and attack that complex. And so when that happens, I get 2 things, right? I get an intermediate which is common to all of these reactions. It's going to go through what we call an rhenium ion. Right, so rhenium ion intermediate, I get that, plus iron tetrabromide, which is going to be anionic. Right, it's got a net negative charge. All right, any questions so far? All the arrow pushing and stuff, we've seen it before, right? We've seen alkenes act as nucleophiles and attack electrophiles, so it's nothing special about that.
That's supposed to be a 4, Dr. Russell?
Yes.
All right.
You're trying to talk about my handwriting on a Friday? Man,
No.
I thought we was better than that. All right. So this is where we are after the nucleophilic attack of the ring. Remember, this is electrophilic aromatic substitution. So we're adding an electrophile to the ring to substitute for one of the hydrogens, right? So the ring is my nucleophile. So the ring acts as a nucleophile. And then in the 3rd step, we're going to reestablish aromaticity. Let me do this too, because there is a hydrogen here, and we're going to remove it and put a pop and make a pi bond. What is that process called when we form a pi bond? What's the easiest way to do that?
Resonance?
That's one way. But we don't have any. We have a in order to do resonance, you got to have a donor and an acceptor next to each other. You got an acceptor, which is that plus charge, but you don't really have a donor to give it a pair of electrons. So, well, I guess you do over here, but you don't really see resonance in this system. I guess you do have like an allylic type arrangement right there, but you're not going to see that because that's just going to move the plus charge around the ring. But there's another way to do it that we learned.
Is it deprotonation?
Yes, we're going to do an elimination. So in order to do that, we're going to reestablish the aromaticity. Right? One of the things about the aromaticity is that when you break it up, you lose a lot of energy, right? And so now that's why you need a catalyst, because it's just, you can't get over the activation energy barrier without a catalyst, which is what the catalyst does. It lowers the activation energy to facilitate the reaction, right? So I'm just gonna copy this and paste it down here. All right, so that's that. And then it's gonna be my iron tetrabromide that acts as the base. Wrong pen. So it's gonna be this that acts as the base. All right, so I'm just gonna draw a pair of electrons from here to here. And then I'm going to put these electrons here, right? So I'm removing that hydrogen, and then I'm doing like an elimination type reaction, right? It would be, if I had to compare it, it would be closer to like an E1 elimination, right? Because you already have a cation, and then now you're pulling off an alpha proton to form a double bond. So that's going to give you this back, right? Plus the catalyst plus HBr. All right, any questions about that? About anything we just did? All right, you're always going to regenerate the catalyst, and you're always going to go through the same 3 steps: activation, nucleophilic attack, and then reestablishment of aromaticity. All right, any questions about it? Let me put a negative sign down here.
We're gonna do some like problems, right?
Yes.
Okay.
All right, and we're gonna actually look at. I want to take this. I'm gonna use the same example. Actually, I want to take this example, and I want to use it to illustrate another concept, which is when you have the ring is substituted, and you do a reaction on it to substitute it again, like the group that's the substituent that's on there is going to control how the new substituent comes in. So let's talk about that. Then we'll go back up top, and I'll show you that section in the handout. We'll discuss it. So if I'm going to take this, and I'm going to paste it here. All right, so this is what I'm starting with. And let's say I wanted to add bromine to it again. Okay, so I'm gonna add another bromine. But now, instead of starting with just the ring by itself, I'm actually starting with the ring with a substituent on it. Now, normally when you think about halogens, you think about them as being electron donors or electron withdrawing groups because of their electronegativity. But if a halogen is attached to an aromatic ring, it's actually classified as a donor, right? So the halogen is a donor, and because it's a donor, it's going to activate certain positions on the ring, and I'm going to show you that through drawing the resonance forms. Sorry about that. Right. So let me show you the products first. We're going to discuss the products and the naming and all that. And then we're going to come back to why we see those products. So if I added another bromine to this ring, I'm going to get two products. One of them is going to be here. And then one is going to be here. I'm going to get both of these products. One of them is going to be favored over the other, though. Come on, B. All right. So those are going to be my two products. So what can you say? Which positions can you say were activated based on the products? Keep in mind, this was already here. I'm gonna highlight this one. That's all that was already there. And then this was already here. So what position got activated? What do you think? Look where the bromine came in at. And then that ought to give you a clue as to what got activated. Is it this site right here? And this site right here?
Yes.
Yeah. So
Okay,
those
but
two.
Dr. Well, never
What?
mind. I was gonna
Go
ask a
ahead.
question. So I was gonna say, why did you do cis and trans products? But now I see because it's two bromines, right?
Yeah, but they're not cis and trans because the ring is flat. So they both on the same face because it's all planar, right? It's and the fact that it's a ring means that there's not going to be necessarily a cis and trans because all the double bonds are locked, right?
Okay.
You see cis and trans in a traditional sense when you have an unlocked, like an acyclic molecule like that, right? So that would be trans and that would be cis. You following that? But because this ring is all pi bonds and it's all locked up, there's no cis and trans. But the fact that we have a substituent on the ring before the reaction, it brings up another idea, right? So let's talk about that. So if I have a substituent on the ring, and I'm just going to say X, if the ring is already substituted, right? The positions on the ring, they change, right? Normally we use numbers. We say this is position 1, this is position 2, 3, 4, so on and so forth. In this case, we use terms. If it's going to be a di-substituted ring at the end of the reaction, everybody agreed that these rings on this side have two substituents. Got two bromines.
Yes.
So yeah, so this is what we call di-substituted. Let me see if I can spell today. I hate, this is my least favorite word in the English language is substitute. It's just too much. It's a lot going on. So if I have a ring that's already substituted, the positions here, here, and here are the positions that can be substituted because on the other side it's identical, right? So that position that's highlighted in yellow, we call that the ortho position. And the one in brown we call meta, and the one in green we call the para position. Right. So up here you can see that the one of the bromines went where? And let's say for the top product, where did that second bromine end up?
The meta position.
Look at it again. Ortho, I mean, meta would be like a 1. Let me put some numbers in.
Ortho.
If I have
Ortho.
yes.
You said all highlighted positions can what? Can
Say
be
that again.
substituted. You said that all the highlighted positions can be what?
Can be substituted.
Yeah. Okay.
Mhm. Right. So let's use numbers. Right. So look at the arrangement of the two bromines in the top product. What would you say the arrangements was if you used numbers? Would it be 1, 2, 1, 3, or 1, 4? In the top product right here.
1, 2.
It's 1, 2. So that would be that arrangement we call that the ortho arrangement, right? Because you can see right here, the ortho position is right next to the substituent. So that would be 1, and that would be 2. But we don't use numbers, we just use these terms. All right. Is that clear? Anybody not see it?
Because then the one below that'll be the 1, 4. So that'll be para.
Yes. So this one right here, you can see the substitution is 1, 4 type substitution. So that's the para product. So when you have a halogen on the ring, like we have here, or some other donor on the ring, it's going to favor 1, 2, and 1, 4 addition. And I'm going to show you why. Right? Because we just said the halogen was a donor. Everybody agree with that? And before we go further, what is a donor? What is it donating? Money, clothes to
Electrons,
you.
right?
Electrons. It's donating electrons. Good. All right. So if you have a donor on the ring, let me just sum that up. Prior to the reaction, it's going to be ortho, what we call ortho para. Dang it. Directing. Oh, let me shrink that down some. All right, are y'all following that? So if I have a donor attached to my ring before I do any reaction to it, anything that comes in, any electrophile that I add to that ring is going to be added at the ortho position or at the para position, right? You get those two products. Which one do you think is going to be favored? Just think about the size. Think about sterics. Which one do you think is going to be favored?
Okay, Dr. Russell, I have a question.
Go ahead.
Sorry, whoever was speaking though.
No, go ahead.
Britt, go.
So just to clarify, when you were talking about the position, so like if like bromine would be on like number 1 or number 2, it would be considered ortho. And if bromine was on number 2 or 3, it would be considered meta. Is that how you said it, or you didn't?
Yeah, no. So you have a substituent already in place, right? And before you do the reaction, right? We started with a substituted ring from the jump, right?
Yes.
Okay. So that automatically becomes position 1, where the substituent is. So now anything that I add to that ring is going to be in relation to position number 1. You follow me? So that's why down here, when I showed the example of a mono-substituted ring, right? The substituent X is 1. So the position next to it by default is going to be 2. And then the position, if you keep going around the ring, you can just count. 1.
Oh, so you started with a substituent? Like
yes.
For up top, bromine would have been 2. 1.
Yes.
Okay.
And so that's why when you bring so now the ring is already substituted. So when you bring in another electrophile, this type of substituent, a donor, is going to force that electrophile either to go to the ortho position, which is position 2, or the para position, which is position 4. It's called activation. Let's see why, and then it may make more sense. Let me add another page. All right, let's go back to the original starting material, which was this ring right here. All right, and we're going back to part 1. All right, if I ask you to draw a resonance form, let me make sure the electrons are the same. Go ahead. If I ask you to draw a resonance form for that, what would you do? Where would you start? Do you see your donor? Where's the donor? Okay. Do you see a pattern of an allylic system with the bromine as the donor and then the pi bond as the acceptor? What if I ask you to draw a resonance form for this? What would you do? And what pattern does that fit? Right, when we study resonance, we had patterns, right? Allylic anion, allylic cation, allylic radical. Which pattern would that fit into with the oxygen?
I'm not sure.
It will fit an allylic anion, right? And so we will push the electrons like this. So the lone pair would be here with a negative charge. And then you can go back to the original like that, right? So when you have a donor on a ring, it's going to fall into the category, it's going to fit underneath this allylic anion type of umbrella, right? This has a lone pair, boom, you push it here, and then boom, push that there, right? So then you can see right away that first resonance form is going to have a pair of electrons. It's got a pair of electrons on the second carbon, which is which position? If bromine is on position 1.
You said what should be number 2?
Yes.
The next carbon over, right?
Yeah. So you see a pair of electrons right here. Is that right? On the ortho position. That's how the donor activates the ortho position, right? So now that's that position 2 right here is now activated. Right, that's activated. So that means when I add my electrophile in, that's one of the places that it's going to go, because the electrophile is going to be attracted to the electrons in the nucleophile, and that's where the electrons are, right? So that's what I mean by when I said that this could only be ortho-para is because when you put a donor on the ring, those positions are the positions that get activated, right? I think we need to, might need to be a little bit of refreshment on donors and acceptors, right? A donor is something that can give away a pair of electrons. An acceptor is something that can accept a pair of electrons, right? And the donor doesn't always have to be, the electrons don't always have to be free. Sometimes a donor can be a sigma bond, right? We're going to see that a little bit later, all right? But that's how I activate the ortho position. What's the next resonance form I can draw? Again, we're looking for that pattern of donor and acceptor adjacent to one another. So here's my donor, and then the pi bond is my acceptor. So what's the next resonance form I can draw?
Can you make a pi bond next to it?
Yeah. Yes, it's the same process, right? It's just going, just different atoms involved, right? If you remember how to deal with allylic anions, right, and you recognize that pattern, the arrows never change. So now I get, not that, this. Right, and I have a pi bond here. Is that right? Yes, no, I don't know.
Yes.
What position is that relative to the bromine that's already on the ring?
Para.
It's the para position, right? That's 1, 2, 3, 4. So that's para. So now you can see, because I have a donor on the ring, the para position is going to be activated. That's my proof to explain why I see what I see up here. All right. Ortho, this is electrophilic aromatic substitution. So I'm adding an electrophile to the ring. That means that electrophile is going to go where the electrons are in that ring. And the fact that you have a donor on the ring, that means that you got your ortho site is activated through it based on the resonance forms, and your para position is also activated based on resonance. Questions about that? Y'all are too quiet today. It's Friday. But that don't mean you have to be quiet.
No questions.
Sure about that. Positive about it. Yeah, so when I have a ring that's substituted, like this one, right? The substituent is going to dictate where the incoming electrophile comes, right? Where it comes into. It's either going, if it's a donor, it's going to be ortho-para. What do you think it'll be for an acceptor? There's only 3 positions that where the electrophile can add, right? It's either going to be ortho, meta, or para. If donors activate ortho-para, then we can kind of extrapolate from that that if I put an acceptor on the ring, it's going to activate the meta position. We're going to talk about it. We got time. And we'll just finish this on Monday. I'll put the test on Monday. Or post it on Monday. Right? I need to put a heading up here too.
Wait, can you say that again? So you said, when
Donors.
you
Go ahead.
wait, now go ahead and say what you was gonna say.
No, go ahead. I want to see how you interpreted it.
You said, okay, it was ortho. I don't know. I don't want to say it, but can you just repeat what you just said, basically, so I can? Please, Dr. Russell, please.
I'm trying to see well, never mind. So if I have a donor on the ring, I'm gonna put a heading up here too, so that if you look at these notes later, you'll know what we were doing. Say reactions on monosubstituted rings, and then the fact that the donor and the acceptor is there, we call that directing effects. So I'm gonna put that down here. If I can write. All right, so when we talk about if the ring is already substituted, if there's a donor on the ring, like a halogen or oxygen or sulfur, or even a carbon-carbon bond, that's going to activate the ortho and the para positions, right? So a donor in the ring is ortho-para directed. It's going to make those two positions hot for electrophile. If I put an acceptor on the ring, it's going to activate the meta position. All right, it's going to activate the meta position. That's what I was saying. So if we say donors activate ortho-para, then acceptors activate meta position, activate the meta position. I always like
okay.
I made the little mnemonic. Is dope in the morning, right? Donors are ortho-para directors, and then acceptors are meta directors. Right? So if we do I want to do this other reaction. Let me see. I think we got time to be able to do it. Where is it? Here. Let's do the acylation. Frito Craft's acylation. At least we can get through the reaction itself. And then we'll use that reaction to do the same thing, to talk about the effects of having an acceptor on the ring. All right, so this is, let me crop that out. Or maybe I can't, never mind. So this reaction right here is the Frito Craft's acylation. All right, acyl meaning the addition of a carbonyl group. That's what that term acyl means. It means the addition of like a carbonyl. You've seen this when we made aspirin and we converted salicylic acid into acetyl salicylic acid. Let me just refresh your memory. We started with that. And then we ended up with this. Right, this is an example of a acylation. So I capped off oxygen with the acyl group. All right, so that's just refreshing your memory. So when we look at the Frito Crafts acylation, let's go through the steps, boom, the 3 steps in the 6 minutes we got left, and then I want to use that to discuss those directing effects too. Right, so I'm starting out with this. What's the first step again in the mechanism?
Activation.
Activation of the electrophile. Right, so I start out with, for the Frito Crafts acylation, an acid chloride, which is a carbonyl. Let's just use acetyl chloride. Right, this functional group that we talked about in part 1 is what we call an acid chloride. Right. And so I'm taking that and I'm going to activate it with aluminum trichloride. Right, and you're going to see the same type of thing happen here. Right, you're going to form like this complex, but in this case, the aluminum trichloride is actually going to rip off that chlorine. Right, some mechanisms show it as just forming a complex and removal coming later, but that's also plausible that that the aluminum trichloride just takes that off, right? And then we can facilitate that by putting a pair, using a long pair on oxygen. So I'm going to end up with this. Right, and oxygen is positive, and aluminum tetrachloride, which, if you remember from the first mechanism, is going to probably come back in and help us do something else later on. So that's the activation part. What about what's the second step?
Nucleophilic attack on the ring.
Good. So my ring is going to attack this. Right, this is my electrophile right here. But I had to make it first in the first step. So now I'm going to take the ring here, boom, plus this. That's positive. And then I'm just going to attack it just like that. Right? And then I end up with this here. Let me write the carbon out, my bad. Everybody agree with that? There's a hydrogen here. And then this carbon is positive. Yes, no? Plus the aluminum tetrachloride, which is going in the next step, do what? What do you think? And this is negative, by the way. The aluminum tetrachloride is negative.
Great.
So step 3 is going to be what?
Reestablish aromaticity.
Yes. So I'm going to reestablish aromaticity. I'm just going to copy this just for the sake of time. And it's going to be the aluminum tetrachloride that comes in. That's negative. All right, I'm going to pull off that proton and eliminate. So that's going to give me this, which is now substituted with a acyl group plus HCl plus AlCl3, because the aluminum trichloride is going to be cycle, right? Regenerated. The catalyst always gets regenerated, right? Is that acyl group? We're gonna stop here and we'll pick this up and finish it on Monday. Is that acyl group that's on the ring? Think that's a donor or an acceptor? Don't answer it. Think about it over the weekend. We come on Monday, that's what we're starting with. We're gonna take that and do another reaction with it. But depending on whether it's a donor or an acceptor is gonna determine how that second reaction goes, right? So think about it, pray about it,
Also,
read about it. Mm-hmm.
so if you're posting the exam on Monday, when is it going to be due? Or do we have to take it like that on Monday at a certain time?
I think I'm gonna post it for a couple of days, but it's gonna have to be done in one city instead of having like stop start. It'll have to be done all at once. So I'm gonna post because I know some of y'all work, so it's gonna be probably have to post it more than one day, leave it open for more than one day, but it's gonna have to be done in one sitting. I think I'll put like 2.5 hours on it or something like that. That's, to give you plenty of time to finish it, but it'll have to be done all at once. So it'll probably be over a couple of days just to accommodate people who have to work.
And it's still gonna be on lockdown.
I'm still considering that because I don't know like how that's actually gonna work with this Black Boy Ultra because I haven't done it before, so I don't know. I don't know if I want to do that experiment yet, but I'm gonna do some investigating today and I'll let you know by Monday.
Okay.
All right. Any other questions? Oh, I'm still putting March. All right. If no other questions, I'll see you all on Monday. I'll make sure I got my days right. I've been thinking the day was Wednesday.
I actually had a question.
Okay, go ahead.
This is off topic. It's about the in-class handouts.
Mm-hmm.
Those are a part of our grade, correct?
You mean turning them in with
Yeah, turning them in.
Yeah,
Oh,
absolutely.
okay. I had submitted one of them. Well, I didn't submit the rest of the worksheet, and we only had one attempt on it. So I was wondering, like, could you reopen it so I could submit the rest for it?
Yeah, send me an email, and I'll clear it out so you can put the right thing in there.
Okay. All right, I will.
Yeah, I'll just send me an email and remind me.
All right, thank you.
No problem.